All right, so now here we are. Derivatives are called rates of change. So we're going to be talking about how two derivatives are related to each other. So rates are derivatives, related rates. So we're going to be doing implicit differentiation because we have them all as being functions of time. All right, here we go. So we're given a cube's surface area is increasing at this rate. And then what rate is the cube's side length changing when the edge is 3 inches? So we've got a picture of something changing in that instant of time that we're stopping it and taking a photograph. We're wanting to know how one rate is changing given how another is changing. All right, so the given rate is this. So I'm just giving you little indicators. You're going to do ds dt. I'll say for S for surface area is 72. Then you'll want to identify what the rate is you're trying to find. So it looks like a side length. So let's do dx dt is what we're trying to find. And so now my equation better have the letter x and s in it because that's how my derivatives are. So what am I looking for? So s is the surface area. So surface area is 6 sides of area x squared each. Okay, so those letters have to be in. So again, let me emphasize, x and s have to be in my equation. So whatever letters you put here, you have to have in here. Okay, when information, you're always going to save until after the derivative. So I'm going to encourage you to even circle it. So when the edge length is 3 inches, so when x is equal to 3. So now you're ready to take the derivative. So take the derivative of this with respect to t. So let me bring it up here, 6x squared. I'm going to take the derivative with respect to t on both sides. So again, you're doing implicit differentiation. So ds dt. So taking the derivative here, I'd get 12x times dx dt. Now let's put in the information I know. This is 72. 12. Now I can put in the x equal 3. dx dt is what I'm solving for. So 72 divided by 36, or 2, is dx dt. All right, so let's move on to this next example. So air is being pumped into a balloon, a sphere. So you need to know the volume of a sphere because its volume is increasing at this rate. And you're asked to find how fast is the radius changing, and here's the when information. So let's write that down right now. When the diameter is 50, and let's not use that until after we do the derivative. So looks like this is a given rate, so it is the volume increasing. So let's write it as dv over dt is 100. It is positive because it's increasing. Positive derivative means increasing. What are we trying to find? How fast the radius is increasing. So since I already have my equation, I really do need to use these letters. So I need to use r for radius, dr dt. Okay, set to go. Got my equation, my find and given rate. So let me write my equation up here. Okay, so I'm going to take the derivative with respect to t on both sides. Let me just write that. Derivative with respect to t on both sides. So dv dt is, carry along the 4/3 pi as a constant. Take the derivative of r cubed, so that's 3r squared times dr dt. All right, so these 3's cancel, and let's see what I can do to plug things in. So I've got 100 here, so I get 4 pi r. Do I have r? I do. If diameter is 50, then radius is 25 squared times dr dt. So I get 100 over 4 pi times 25 squared. I'm sure that will simplify a bit, but I'm not going to worry about it too much. So that's the rate. The radius is changing. Let's do one more. Okay, So the other two had helps because they were equations that we knew, and you could use letters. This one we have to draw the picture and assign the letters. We need to do it all. All right, so a 10-foot ladder. So a 10-foot ladder is not changing. That's the only number that I'm going to encourage you to put into the picture. It's leaning up against a wall. All right, and the bottom of the ladder is sliding out at a rate of 1 foot per second. So I'm going to encourage you not to put that in the picture, but let's label this side length as something, a letter, and then use that as our given rate. So I'll be really original here. I'll put x here, and then my given rate will be dx dt is 1. This x distance is getting larger at 1 foot per second. All right, so what is it they're asking? How fast is the top of the ladder sliding down? So how fast is this changing? So let's give this side length the letter y. So I'm finding dy over dt. And then the when information, almost always they'll say the word when the bottom of the ladder is 6 feet from the wall. When the bottom of the ladder is 6 feet from the wall, so that's saying when x is 6. Save that until after you take the derivative. All right, my equation. I see a Pythagorean theorem. So x squared plus y squared is 10 squared. Again, the only number that you have in your picture is the fixed number. All right, so let's go take the derivative. So taking the derivative with respect to t, I'd get 2x times dx over dt plus 2y times dy over dt equal 0, because the derivative of 10 squared is 0. The 2's cancel. Now I'm ready to go plug the information in. X is 6, dx dt is 1, y I don't know right now, and dy over dt is what I'm trying to find. So this is the time I use my when information back into my original equation. So if I use 6 inside here, so I get y squared, so that's 36 subtracted, so that gives me 16, 36, no, I mean 100 minus 36, 64, sorry, 64. So then y is equal to plus or minus 8. I'm choosing the positive one because I'm talking about a distance. So solving for dy dt, dy over dt will give me a negative 6 over 8. So the rate is negative for y. Is the length of y decreasing? Is it getting smaller? It is. So that makes sense.